Now we've got a set of worked examples here. This is a set of Edexcel IGCSE questions, courtesy of Save My Exams, and this is the Save My Exams Gold P4. Okay, let's have a look. Question one. We've got a cone here. It's got a slopey side of 9 centimeters, and its curved surface area of the cone is 100 square centimeters. Calculate the volume of the cone to 3 significant figures. So this bit at the bottom here is just drawn from the sort of the front of the exam paper. So we're actually given formulas for the volume and the curved surface area. There we go. L is the slopey length, and H is the height. Okay, so yeah, I mean, sometimes it's quite good to kind of write out a little plan of what you're doing here, and so this is a sort of flow of what we need. So the volume we will need, we can see from the formula, we'll need the height and the radius. Okay, and we're going to be able to get that from, if we've got the radius, we kind of, because we've got the slopey side, we can use Pythagoras to get the height. And we get the radius from knowing the surface area. So we can work back from the surface area using this formula, pi RL, because we know L and the actual curved surface area, so we can get R. So this is a kind of flow, if you like, leading us up to our volume. So let's have a look. Yeah, the formula for the curved surface area, pi RL equals 100, and then we just rearrange that and substitute value 9 in for L. We get a value of R equals 3.537. That's 3 decimal places. That's R, but we also want H as well. So if we just look at the sort of the right angle triangle, is made by the height, the radius, and the slope, then we can say H squared equals L squared minus R squared. So that's rearranging Pythagoras that we've got here. And yeah, 9 squared is 81, and then this is our R squared here. So I've worked that out there and worked out figure for H, which is 8.276. But it could be tempted to actually substitute that into, just carry that forward and work it out in sort of one set of calculations. But it doesn't look as if there's going to be any useful cancellation in there. Plus the fact it's actually quite useful to be able to check this figure 8.276, which seems sensible in relation to the sloping side of 9 and a radius of 3.5. So that's all good. So yeah, we're in a position now where we can just substitute those into the equation for the volume. So that is, from the left hand side, V equals 1/3 pi R squared H. Stick all that lot into your calculator and it comes out with this, actually to more decimal places, but we only want it to 3 significant figures anyway, so that's 108 cubic centimeters to 3 significant figures. So that's number 1. Go down a bit further. Okay, so number 2, simplify, first of all, 16y to the power of 8, all to the power of 3/4. So there's a couple of things coming in here. First of all, we need to recognize that this 3/4 applies to each sort of factor in here. So it applies both to the 16 and also to the y to the power of 8. Also, when we're doing this 3/4, we can break it into bits, and it's useful to use the brackets. So it's 16 to the power of 1/4 to the power of 3. And done it that way, you could actually write it as 16 to the power of 3 all to the power of 1/4. but that's going to involve us actually calculating 16 cubed and a bit more involved, whereas this is nice and straightforward because we can see it's 16 to the power of 1/4. It's the 4th root of 16, so it's going to be 2, so that's pretty straightforward. And then as far as this this bit is concerned, yeah, we just build it. I mean, we can do these in stages, this 3/4, so I've chosen to do quarter first for similar reasons, and then the third, so we can write it like that. So yeah, so what have we got? 16 to the power of 1/4 is the 4th root of 16, which is 2, and then we cube that back up to give us 8. And then what have we got? Because it makes sense, I think, to do 1/4 of 8. So it's y squared, and then that is to the power of 3, which is going to be y to the power of 6. Right, and then that's part A, 8 times y to the power of 6. Part B, given that 2p plus 8, 2 to the power of p plus 8 to the power of q equals 2n, express n in terms of p and q. Right, well, key here is if we can express this to a power of 2, and then we can put both of these together, then we've got an equation in n. So let's have a look. 2 to the power of n equals 2 to the power of p. Yeah, 8, of course, is 2 cubed, so we can write that like that. To the power of q, and of course we can rewrite that as 2 to the power of 3q, and then we've got 2 to the power of p times 2 to the power of 3q, and that is 2 to the power of p plus 3q. So so we can see from that that n is equal to p plus 3q. N equals p plus 3q, and that is part B. Right, so let's go down to number 3 now. This is a vectors question. If you don't get vectors, then I suggest you have a look at my video on vector geometry. Okay, so what we got here? Right, okay, I'm going to see sort of rectangle. We've got diagonal, and we've got this line extended here. OPQR is a rectangle. D is the point on OP such that OD equals 1/3 of OP. OD is 1/3 of OP. So that's kind of saying to us what this vector OP is. And because this line is 3 times the length of OD, and it's in the same direction, so this is going to be 3A. Anyway, that's jumping ahead a bit. E is the point on OQ such that OE equals 2/3 of OQ. That's so that's 2 to 1. If we look at it as a ratio, 2 to 1. PQF is a straight line such that QF equals 1/3 PQ. So that's that is 1/3 of that length. We don't yet know this vector PQ, but we're going to find that out, I'm sure. So, and OD equals A and OR equals 3B. Find in terms of A and B OQ. So that's A part 1. OQ, right, we can expand our OQ. So just look at it a different way. Is if we want to get from O to Q, then we can do it by going along this route, OP plus PQ. Now we've got to kind of use a bit of imagination because we don't know PQ at the moment. We don't actually know OP directly, but we did observe before that OP is actually 3 times OD. It's 3 times the length in the same direction, so that's 3 OD. And the other thing is because PQ and OR are the same length and parallel, then they have the same vector value. So let's use OR instead. So now we've got OQ in terms of things that we have a value for. So that's 3A plus 3B. So OQ equals 3 into A plus B. OE is the next one we have to find. That's down here. OE, well, OE E is on a point on OQ such that OE equals 2/3 of OQ. Right, okay, that's a point on the line. So obviously OE and OQ got the same direction. So OE equals 2/3 of OQ. And we know OQ from part 1 of A to be 3 into A plus B. So therefore, we can just calculate that as 2 into A plus B. The third one, which is kind of off the page there, but is to find DE. Right, okay, well, again, you know, for a start, we need to kind of look at things that we know. DE, well, you know, we know this one here, and we know OE as well, so we can just put it in terms of those. So yeah, DE expanded equals DO plus OE, and note this expansion, you know, we've got these two adjacent letters here and sort of form a bit of a cancellation. So DO plus OE, DO is minus OD. All right, so it's the vector in the opposite direction. So we change the sign. So minus OD plus OE, so that's minus A plus 2 into A plus B, which we've got from here. And that gives us A plus 2B. Okay, so yeah, I mean, those things are fairly straightforward, really. Okay, part B is a little bit more difficult. Let's see if we can get it all on the screen. The use a vector method to prove that DEF is a straight line. Let's see. Let's just do that. DEF is a straight line. It's not accurately drawn. It doesn't actually quite look at that, but we can see that these are a straight line. Now, this is actually where vector geometry is quite useful, because if you try and prove that without vector geometry, I'm not actually sure how do it. There will be a way, probably similar triangles, but it's pretty straightforward actually with vectors. So let's have a look. We can prove things are a straight line if we take two pairs of points. If the vectors are scalar multiples of each other, then they must be parallel. And of course, because we've got a common point involved, then therefore they must be collinear if they are also scalar multiples of each other. So we've got DE. So if we actually evaluate DF, we could do EF. And DF is arguably slightly more straightforward. So DF equals DP plus PF. Again, notice these adjacent letters here are the same. So this is more or less the same thing as saying if we want to go from D to P, we can go D to F, go D to P, and then P to F. So that's what that's saying. Now DP, well, it's 2/3 of this whole OP thing here, isn't it? So that's actually two ODs, 2 times OD. So it's twice the value of vector OD. And then PF is going to be PQ plus QF. Right, PQ is 3B, because we've established it's the same as that. And QF is 1/3 of this length. So it's going to be plus another B. So that's going to work out to be 2 into A plus 2B. So now we can see that DE and DF are scalar multiples of each other. DF is in actual fact twice of DE, 2 times. So they're scalar multiples and they share a point, so they must be collinear. And that means that DEF is therefore a straight line. Okay, so that is that question 3. Right, let's go on. Now we've got a geometry question. So this is to do with similar figures. We've got these two triangles here. This PQR is an enlargement of this smaller triangle ABCD. C. We've got all the lengths there, they're all written down there. So the first thing we've got to do is work out the length of CR. Now, there's a couple of ways we can do this. So the way I've chosen really is to look at OR. I mean, what we've got here is this is scaled up. So for the lengths really are in the ratio of 3, not to 12, but to 15. Remember this, you know, when we go from this point, this triangle has been built up from some kind of, you know, sort of growth by 3 centimeters. You can imagine it's sort of infinitesimally small sitting at the origin. We've grown it by stretching it 3. This big one we've sort of pushed out by 15. So the scale factors, all the lengths on these triangles are in the ratio of 5 to 1. 1 for the small one and 5 for the big one. Okay, didn't quite look it because the diagram is not accurately drawn, but that's what we've got. So that's something just not to trip over. It's 5 to 1, not 4 to 1. So we're looking for OR in the first place. So let's have a look at the ratios here. So OR to OP is equal to the ratio of OC to OA. Yeah, we can write that or cut that in different ways, but that's the way I've chosen to do it. So just changing that round, we're going to get OR equals OP times OC over OA, which is this number here, which gives us 17.5 for OR. Take away the 3.5, and that's going to give us CR equals 14 centimeters. Work out the length of AC. Okay, well, I think we just sort of said that the scale factor involved in these is 5 to 1. Okay. Well, this is sort of just how we've written it as the ratios. You could write it like that, but essentially it's 5 to 1. So this is going to be 1/5 of the value of 19, 3.8 centimeters, in other words. Right, so we'll establish the scale the factor as a ratio, 5 to 1. That's what we call the linear ratio. Now, if the linear ratio is 5 to 1, then the area ratio, it's not 5 to 1, but it's 5. It's 1 squared to 5 squared, or 1 to 25. So this triangle here has got 25 times the area of this small triangle here. Okay. Yeah, so we're actually given that area of ABC. So obviously the bigger one is 25 times the size, so that would be 50 square centimeters. Now, so this is worth noting. The area ratio is the squares of the linear ratio. If it was a 3D problem, by the way, then not only would we, you know, if we had corresponding volumes to think about, then there'd be in the ratio of 1 cubed to 5 cubed. And those problems come up quite a bit, where you're given the maybe the ratio of the surface areas or something like that, and then you have to work back to the linear ratio and cube it back up to get the volume ratios. Anyway, not in this particular problem, but that is number 4, and again, sort of fairly frequent type of problem to do with similar figures. Let's wind down to this one. This is a cumulative frequency graph. The cumulative frequency graph gives information about the length in minutes of 80 telephone calls. Okay, so we don't know how this has been built up, you know, what class intervals we've got our data from, but, you know, we've taken that that information and plotted it on here, and then we've drawn it with a bit of a curve, because quite often you might see these sort of as a series of straight lines, a bit easier to draw. But this has been turned into a curved line, which is probably more reflective of the data. But if you do get these to draw and you give them actually the class widths and frequencies with the class widths, then you could actually do it with straight lines. Okay, so so this is a typical sort of cumulative frequency graph where we get this so-called S shape, and the reason for that is we tend to find that the a lot of the data it happens in a relatively small interval. In this case, we've marked off the interquartile ranges. So most of the telephone call number figures that we've observed are actually going to be falling somewhere in the middle, and at the end we're going to have the more exceptional kind of cases. Okay, so what is it asking us? It says find an estimate for the number of calls. We should say that were longer than 15 minutes, but okay. Right, so if we mark on 15 minutes here, take that up to the cumulative frequency graph. Okay, so what it's sort of saying is that all this lots in this area here are ones which are greater than 15 minutes, up to 30 minutes, in fact. And everything that's in this area here represents the calls that are less than 15 minutes. So anyway, so obviously the kind of dividing point is here at 72. So what we're concluding is that there are, out of 80, there are 72 that are going to be less, and therefore 8 that are more than 15 minutes. Now that's our estimate. We don't know the exact data at this point. We've sort of discarded that in favour of this sort of summarised version. So that's what we're estimating, 8 calls. Then it says find an estimate for the interquartile range of the lengths of the 80 calls. Well, the interquartile range is the range between the 2 quartiles, and since we've got 80 telephone calls, then the lower quarter of 80 is 20. The upper quartile, which is 3/4 of 80, is at 60. The median, of course, is the 50th percentile, and that would be at 40, but we're not actually interested in that on this particular problem. So this is the interquartile range. So these are the number of calls, and this is the range that is of length of calls that are in that middle 50%, isn't it? 25% to 75%. This value is 6. This value is 11, and the difference of that is 5 minutes. Okay, so 5 minutes is your answer. And what this means is that 50% of the calls are in this gap. And yeah, just reflecting what we said before about you know, kind of a lot of the data tends to be around the middle, and then we get more exceptional things spread out at either side. So that is number 5, cumulative frequency. Right. Okay. Now, there's a question on regular polygons and angles in regular polygons. This diagram shows 2 congruent regular pentagons, 5 sides, and part of a regular n-sided polygon A, 2 sides of each of the regular pentagons and 2 sides of A meet at the point P. Calculate the value of n. So, well, we can see that if we put these 2 angles from the polygons together with this one angle from this polygon of n sides, then that's basically 360 degrees. So I think the point here is that what we're doing is if we can find out what this angle is, we can then find out what the how many sides the polygon has got. And in order to find out this angle with the blue dot, then if we know the interior angle of a pentagon, we've got two of them together here, then we will, we'll know what the two red ones add up to. So the internal angle of a regular pentagon. Okay, so and we do this 5 sides. We split it up into triangles and count the number of triangles, then that'll give it to us. And there's always 2 fewer triangles than there are sides on your polygon. So there's 180 degrees in each triangle, and of course there's 5 angles. So 5 minus 2 times 180 divided by 5 gives you the size of the internal angle of a regular pentagon. So this polygon here has got an internal angle of 360 minus 2 times, well, it's this one and this one, isn't it? 2 times 108, and that's 144 degrees. Now, if we apply this same formula here, the same idea of number of sides minus 2 times 180 over the number of sides, then we can actually use this 144 degrees. So what we have to do is say, let n equals the number of sides of the polygon. Well, we're actually told that anyway. So the size of an internal angle will be n minus 2 times 180 over n, and that is equal to 144, because that's just what we've calculated. So then we got a little equation in n. We multiply the n up to here, work that through, we get that n equals 10 sides. So that is a decagon, isn't it? So, yeah, okay, so that is number 6. Number 7. Right. Okay, we've got a circle, a couple of triangles. B, C, and D are points on a circle center O. BOD is a diameter of the circle. Yeah, BOD, so this is a diameter here. AB is a tangent there. Yeah. Which tells us that this angle here, ABD, yeah, that's a right angle as a result of this being a tangent. This is a tangent, this is a diameter, so this is a right angle. AO equals 8, BAO equals 30 as shown, CBD is 63, calculate the length of BC. Okay, so again, little kind of plan. We can get BC if we know BD. We can use SOHCAHTOA then. Or should just say that we need to note as well, because this is a diameter. This angle here is a right angle. So that's an important circle theorem fact, actually. So we need to know that as well. So therefore we can use SOHCAHTOA in order to find BD. And if we know OB, then we can double. Yeah, these are both radiuses. So we'd like to know OB. Well, we can find OB using SOHCAHTOA from this triangle. So OB over OA, OB over OA is equal to sine 30. OB equals OA sine 30, and OA is 8, and sine 30 is 1/2. That's one of those trig ratios that you should be able to recall pretty quickly, because it comes up quite a bit. So OB is 8 times 1/2 equals 4. So if OB is 4, then OD is 4. Therefore, BD, rather than OD, as it says there, BD is actually 8. So we're going to then use that 8 together with this 63 degrees, because the cosine of 63 is BC over this 8. So I've written OD, but actually means BD. 63 BC 8 times cos 63, and therefore BC equals 3.63 to 3 significant figures. So that's number 7. Okay. What to do? Population of India increased by 20% between 1989 and 1999, and again by a further 17% over the next 10 years. Calculate the percentage by which the population of India increased over the whole 20-year period. So 1.2, 1.7. So what we kind of best looking at with this sort of thing is the growth factor. So the growth factor is the sort of multiplicative number, which when we apply it to the original population will give us the population at the end of that period. So whatever that population was, we multiply by 1.2, and then we're going to do the same thing with the second 10 years. So therefore, the growth period over this 2-year period is going to be the product of these two. So it's going to be 1.2 times 1.17, which works out to 1.404. So this is the growth factor for the 20-year period. And that, of course, when we write that as a percentage increase in the same way that we've got 20 and 17 here, then that's actually going to be an increase from our original 100% to 140.4%. So the actual percentage increase is the difference between the 140.4 and the 100, which is 40.4%. Okay, so I hope that's, yeah. I got another one with indices here. Simplify 3a squared b all to the power of 4. Well, as before, got to notice that this 4 here applies to each of the factors inside the bracket. So it actually gives us 3 to the power of 4 times a squared to the power of 4 times b to the power of 4. A squared to the power of 4, this is a times a, isn't it? And then we're doing that 4 times over. So it'll be 8 times a times a times a times a times a times a times a. That's obviously 8 a's, so that's a to the power of 8. So 3 to the power of 4 being 821. 3 squared squared, another way of looking at it. So that's 821, a to the power of 8, b to the power of 4. And then the part B, simplify 9c to the power of 8 to the power of a half. And again, this half applies both to the 9 and to the c to the power of 8. So we've got 9 to the power of a half times c to the power of 8 to the power of a half. 9 to the power of a half is the square root of 9, and that's 3. And c to the power of 8 to the power of a half. Well, we multiply these two together, don't we? That gives us c to the power of 4. So that is 3c to the power of 4. Right. Okay. So those are pretty easy 4 marks there. Right. And finally, question 10. Right. So this is an interesting one. So we've got to see what's going on here. We've got a circle. We've got this is a diameter extended out to here. And then this line up here, these two are the same length. Okay. A, B, C, D are points on circle center O. Yep. So this AB is a diameter, therefore. A, O, B, E, and D, C, E are straight lines. Yep. CO equals CE. Those are marked with those lines there to signify that. AOD equals 69 degrees, and angle CEO equals X. Calculate the value of X. Okay, right. Well, we're given quite a lot of information here, actually. So let's just kind of work through. I mean, we could sort of do a plan back from what we need to know. We kind of could do that, but sometimes it's just, you know, these things are best done just by, let's just fill out the things that we know and just work through it that way. So what we got? Well, COB. So this is isosceles. So this is X as well. So I'll mark that in up there. That's X. And therefore we know what this OCE is. This angle here, OCE. Mark that in there because that's going to be 180 less these two X's, 180 minus 2X. And therefore this side of it, DCO, OCD if you like, is going to be 2X. That's 180 minus this 2X. Right, so the next bit is perhaps a little bit, it's not obscure, but what we've got to note is that these two, OD and OC, are both radiuses, radia. So this is an isosceles triangle. So therefore, the value of this angle D here is the same as this one. So these are both 2X. Well, these are both 2X. Then this one here, this is the angle subtended by this chord at the center, is 180, being the total angles in a triangle, minus these two other angles, which come to 4X, 180 minus 4X. So along this straight line then, we've now got 69, 180 minus 4X and X. So we can put that in our equation because obviously angles in a straight line add to 180. So we've got an equation in X. This is pretty straightforward to solve, given as X equals 23 degrees. Okay, so I think there are just a couple of things to note here. First of all, it's sometimes sort of easy to kind of miss the fact that, you know, that something's a radius and, you know, therefore, you know, a triangle is isosceles. It's not too difficult, but it can be missed. The other thing is that we don't expect to be able to calculate this by actually just filling in a load of values. You know, this is 69, therefore this one is some number, or, you know, these things are made to test your algebra as well as your geometry skills. So so this we can expect to form some equation in X, and that's exactly what we've got with this equation here. So with those two things in mind, you know, armed with those thoughts, you shouldn't have a problem doing this. Okay, so that is that. Hopefully you've found that useful going through those questions. A lot of these things are typical of the sort of things that you get in an IGCSE exam. So so if you can understand the working through here, then that's half the battle won. But obviously you have to take that understanding and test it out by doing your own examples. There's no reason really why you can't just lift these things and work through them. Having seen the solution, it's still quite helpful and useful to maybe have a go at it yourself. But obviously, you know, don't allow yourself to be prompted by this worked solution. Okay, so that's it, and thanks for watching. See you next time.